when we first started doing line integrals in 13.2, right, which seems forever ago, line integrals over vector fields, this was work. This was us computing work. And so this was the formula for work. This was the notation for it. We said we had to have a field, we had to have a curve, we had to have a parametric representation or a vector function that drew the curve. We needed to know the limits on t, and then what we'd do is we'd compute this right here. So you just had to evaluate the field on the curve and dot that with the derivative of the parametric representation of the curve. And this was just another way of writing the same thing. We didn't get too much into that. So now we have Stokes' theorem. Let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with positive orientation. Okay. What are we saying here?
This curve is connected into a function.
Line integrals, right? In three-dimensional space. If we're asked to do a line integral, our curve C lives in three-dimensional space, right? If that curve is closed, right? If it's a closed curve, and we orient it in a way that when we walk around the curve, the surface is always to our left. So imagine that you're walking counterclockwise around the curve and that our surface is always to our left side. Positive orientation will be upward. What I want you to see is that curve encloses a surface. This is weird. I mean, I can give you a very simple example. If I just draw a circle, let's say this is the x, y, z. If I just draw a circle that's parallel to the xy plane, then obviously that curve encloses a surface, right? And that surface would just be like a disk. But this is saying more generally that if that curve is closed, then there is a surface enclosed by that curve, right? Where that's the boundary of the surface. So what's happening inside of here can be kind of anything. I'm trying to think of a good analogy. Imagine you have a drum, okay? The boundary of that drum surface, right, is a curve. The drum itself is a surface. But if I push my hand down on the middle of the drum, it'll warp in, won't it? But that's still a surface with the same boundary. This theorem says regardless of the surface in here, as long as this curve is the boundary of that surface, we have this, which is just mind-blowing if you really think about it. It says if you want to calculate the work as you move through the vector field around the curve, then all you have to do is calculate the surface integral of the surface that is enclosed by the curve, or bounded by the curve, but you're not doing the field, you're doing the curl of the field dotted with the normal vector ds. So we somehow turn a closed line integral into a surface integral. Just like Gauss's theorem, or the divergence theorem, allows us to turn a flux integral into a triple integral, right? This allows us to turn a line integral into a surface integral. So, what's that? This is Green's theorem in three-dimensional space. So in Green's theorem, right, we were on a flat sheet of paper, and we said as long as our curve encloses some area here, then we can do the double integral, but then we had to do like partials, right? Something about the partials in there. Well, those partials actually come from this idea of the curl. So let me continue. Remember that the curl of a vector field is this, right? This thing, and then we do our little thing, and this is what it came out to be. And you're recognizing this right here. This is, in two-dimensional space, this is that part that went into Green's theorem. That's it right there. But now we have, in 3D, we have the whole thing, the whole curl to deal with. All right, so let's take a look at an example. Let's find the line integral. So find the work done, in other words, by the field on some object moving over this curve, C, where C is the triangle with these vertices, and notice we're in three-dimensional space. So Green's theorem would not work here, right? So I'm going to draw my curve. So 1, 0, 0, 1, 0, 0, 1. 1, 0, 0, 0, 1, 0, 0, 0, 1. And my curve is that, right? So I move around this thing, okay? Well, is that curve the boundary of a surface? It is, right? It is the boundary of a surface. It's the boundary of this surface here. All right? Since it's the boundary of that surface, S, I can turn this line integral into a surface integral. So this line integral will be equal to the integral, the surface integral, which is a double integral, of the curl of F dot n ds. All right, so this is just using Stokes' theorem. Okay, using this right here. Now we could also just use this. I'll write them both down so we have them. All right. Maybe we should start with the curl of F, just to see what the curl of F looks like. All right? So how do we calculate the curl of F? We have to do this partial with respect to x, partial with respect to y, partial with respect to z. And then down here we put the field, which is x plus y squared, y plus z squared, z plus x squared. And then we do kind of like that determinant type thing, right? So, or cross product, I should say. I don't know why I said. It is determinant. That's a determinant right there. So what will that part be? Partial with respect to y of this, which is 0, minus partial with respect to z of this, which is 2z. So minus 2z. And this is a vector, yes? Minus 2z, comma. Now we do the middle one. And I'm going to do it backwards. Here to here, which is 0, and then minus here to here, which is 2x, and it's positive or negative? Negative 2x. And then the last one here, go here to here, which is 0, and then minus 2y. Okay? So that's our curl of F. Now, which of these would you rather use here? This one or this one? We know the curl of F, right? Do we know the normal of our surface? Well, we don't, not right away, but do we, does it change?
No, it's not.
Because it's a plane, right? So whatever the normal is, it's always the same normal.
And you can
Agreed?
find the vectors between each of the points, and then using that you create your equation.
That's right. We can come up with the equation of this plane, which we can generate the normal vector of this plane, can't we?
Yeah.
So let's take the time to do that, because I think it would be worth it for us if we just grab the normal off of this. And be sure that when we do it, we grab the unit normal. I mean, we're going to grab a normal vector, but we need to make sure it's a unit normal vector. So why don't I go, say, here to here, here to here. So we've got 1, 0, 0. This is 0, 1, 0. And this is 0, 0, 1. So let's make that vector 1, and let's make that vector 2. We've done this so many times, yes? So what's vector 1? Negative 1, 0, 0. And then what about vector 2? negative 1, 1, 0.
No, that's a wait, that's not, vector 1, that's not right. What was that?
What's not right?
Vector 1?
Oh, negative 1, 0, 1.
Yeah, it's negative 1, 0, 1.
Negative 1, 0, 1. Okay, good. And then vector 2, is that right?
Yeah.
Okay, now we cross those. So when we cross these, we get 0 minus 1, so we get V1 cross V2, negative 1. Let me double check that. 0 minus 1, and then here, the middle one, negative 1, right? Negative 1, and then nothing, so just negative 1 again. And then when we do our last one, we should get negative 1. Is that all right with you all?
Yeah.
Okay. Now, what's the length of that vector? Square root of 3, right? That's how long it is? So if I want a unit vector, I need to take this and scale it, right? I also would like to make sure that if I were to travel around my curve, the way we travel around, when we're traveling around our curves, we always want to have our surface to our left. Okay, so we would need to go this direction, right? Do you all agree with that or not? This is kind of important because we're in three-dimensional space now. So if I was kind of standing here with my head right here, as I walked around, the surface would always be to my left, yes? If I went to the other side and was standing upside down, then what? What would happen if I start moving this way?
You have to move the opposite direction.
I'd have to go the opposite, right? Sure? Let me do it this way. Okay. Okay, so if I'm right here and I'm walking around like this, that direction with the arrow, the surface is always to my left, right? Yes? Okay, let me flip it over. Okay, so now if I walk this way, the surface is always to my right, yes? Okay. So when we say positive orientation, what we mean is we want the normals, we're basically walking on the surface, we need the surface on our left, and then the normals will be pointing upward like this. Does that kind of make sense? So is this vector going to work? Because which way is this one pointed? Inward, right? It's pointed in. It's like almost like a center-seeking vector. So we need to actually change this to 1, 1, 1, and we need to scale it to be square root of 3. Yeah. So the normal that we're going to use is going to be 1 over root 3, 1 over root 3, 1 over root 3. That normal will satisfy the conditions for Stokes' theorem.
And you got the root 3 by?
Dividing by its own length,
Got it.
right? Okay. Where are we? So I'm here, right? Okay, so this, doing the surface integral, I have curl of f, which was negative 2x, 2y, 2z, dotted with the normal, which is 1 over root 3, 1 over root 3, 1 over root 3, ds. So what have we still not accounted for here? That we can dot easily, right? What have we not accounted for? The S itself, right? Like this is the field in the normal, but we need the surface itself. So when you look at that surface, can we actually define this surface? Can we come up with some way of drawing that surface? So you have to ask yourself, is there an R of UV that will draw that? There is, right? But isn't that a special case also? Isn't that surface a function of x and y? So right now, what we're at, the point that we're at right now is kind of like where we started the class today. This is kind of like f dot ds. This was flux, right? Okay. But instead of using f, we're using curl of f. So that's different. But at the end of the day, how we do it's the same. So can we continue here then? I want to point out that this right here, what is the equation of that plane? Can you tell me the equation? We've already done all the work for it. I'm going to use the vector 1, 1, 1 instead of -1, -1, -1. So where am I getting that from? 1 times x minus x naught plus 1 times y minus y naught, but I'm using this point right here, 1, 0, 0. Okay, so this is our plane equation. So I can just simplify, and then I can solve that for z. And now I have that plane defined, z is a function of x and y. Okay? So now I can go to which formula on this, on that handout I gave you. You're now looking at which one are we on here? F. F, right? We're in formula F here. Because, remember, we have a vector field, right? This is our field. This is our P. This is our Q. This is our R, right? Yes?
Yeah.
So, try and think of how we want to go about this. Let me ask you something. Because there's two ways to look at this, so I'm curious how you interpret this. What about formula B? Look at formula B. Let me erase this real quick. If I dot these together right now, if I dot those together, am I going to get a scalar function? That will be a scalar function, won't it? And look at B. It's the double integral over S of a function of x, y, z, which I would get when I dot those, right? And then the square root of the partial of g with respect to x squared plus partial of g with respect to y squared plus 1, right? Do we know what g of x, y is? It's this, right? That's our surface. So we could use f, but the problem with f is that we have to back up and redefine our field because our field is the curl. So I'm going to go and use b because we have a scalar function right here. So I'm going to go straight to that formula. So this is g. This is g of x, y. So I'm using formula b. So this should become, let's go ahead and dot that. It's double integral over d. Okay, our scalar function, we got to dot these. So -2 over root 3x minus 2 over root 3y minus 2 over root 3z. And I'm going to multiply that times what? Square root of partial of this with respect to x, right, which is -1 then squared, plus partial of this with respect to y, but squared, plus 1 dA. And you see that root 3? That root 3 is going to go through and kill off all those other root 3's. And I still have one more thing to do before, well, a couple of more things to do before I integrate here. I'll pull a -2 out, that's fine. The root 3's are gone, yeah? So this will become x plus y plus z, but z is 1 minus x minus y. Right? Which is dA. Okay. So this is 1?
Yeah.
Y'all agree? And I heard some happiness there. This is negative 2 integral over d of 1 dA. Right? Which is the area of what? What triangle? D is the xy plane. So it's the area of that one on the bottom. That's D, right?
Yeah.
Do we know the area of that?
We can easily figure that out.
Yeah, I mean, it's a triangle. We have, 1 here, 1 there. So that's 1. So half of 1 times 1, right? Which is a half.
Yeah.
Okay, so this is equal to negative 2 times a half, so you get negative 1. Whew. Not quite sure that seemed easier. I mean, your other option for this one, if you didn't want to use Stokes' theorem, would be you'd have to find a parametric representation of the curve. So you'd have to find like 3 separate line segments, and then you'd have to work your way around. Could be done, but, Okay. Why don't I let you work on this one? I'll help by getting the drawing of this down. You're trying to find the line integral over the curve C, where C is the circle x squared plus y squared is 16, with z being 5. That's your curve? That's your curve C? It's a circle of radius 4. It's a circle would normally be in the xy plane, but we're fixing z to be 5, so it moves it up. So that's our curve. And let's use Stokes' theorem on this. So what we want to do is look at the surface that thing is the boundary of, and then do your surface integral instead of your line integral. All right? So go ahead and we'll take, 15 minutes? See if anyone can get to the end of this problem. You might want to just start with the curl. Like, take a look at the curl, see what it looks like, and then go from there.
basically, when you're speeders first, you would have here to have respect to y, and that was an x, so just be equal to x, y. And then that's for speed 3, that's it. So, like, this makes sense.
Okay, okay. Why is the derivative with respect to?
That's 0, it's constant.
Yeah, so they all be 0.
Yes.
All right. So look how this is.
Hold on though, no.
No?
Okay.
Are you calculating the div?
Yeah, we're trying to do the curl.
It's curl, not div.
Yeah.
You have to do cross product.
Yeah, you do cross product with that, that's the thing.
Yeah, if this were div, then that would be something different, right?
Oh, yeah, okay, yeah, I'm right.
Yeah.
So, yeah, it's
Yeah.
different, so.
You're trying to use this, so you've got to calculate the curl of f,
Yeah, so
which is
derivative-
a little more
derivative of each
complicated.
one. So derivative of that would be, the first one would be 0, which is x.
I'm just turning that off for a second. I'm leaving everything else up there for you. I got to look at something real quick. If you get an answer, because you might get it pretty quickly, let me know.
So I got this far, finding the curl
Okay.
and the normal.
Yep.
Would you turn that z into 5 just because that stays?
Is that 2x minus z that you have there?
Yeah.
Show me how you got that. That last component. By the way, cover the last one.
sorry.
Yep. No.
Oh, it is 2z. Okay.
Okay. Yeah. 2z minus.
Okay. So
There you
I
go.
wrote that originally, and for some reason I thought it was x.
Yeah. No. It should be 2z
I
minus
was
z.
looking at that. That's why.
Let me double check it, but I'm pretty sure that's right. It's just z, right?
So it should be 5,
Yeah.
and it would be 5.
Now that domain down there is still s. You're doing
Because I haven't changed that to.
because all you've done these little things are tricky. I understand the notation, but the notation's important. All you did was this step right here. You did that, dotted with that. So you're still at this stage of the game, okay? The way to get it to DA would then, not to DA. Yeah, DA here and D here. The way you do that is you'd have to figure out what your restrictions on X and Y are, which you don't need that. You actually don't need it because you're saying what's the area of that surface. Yeah, 5 times the area of that. It would be the same answer if it was projected on the ground. What I'm getting at is, let's say like on the ground you have the circle, right? And up here you have the circle. So the area of this is actually equal to the area of this.
Right.
But let's say that this was like some weirder shape, like, did something like that.
And Z wasn't constant.
Z wasn't constant.
So how, okay, so
Yeah.
I'm right here.
Uh-huh.
If I wanted to
Keep going.
keep going to D and DA,
Yeah.
how would I do that? Would I just do like, and then have to find?
You would do this right here.
I would change it to U and V?
You would do this right here. Yeah, I would use this one right here. Okay, but your function there is 1, right?
Mm-hmm.
And so ds is that. Okay,
It would be 1.
which would be 1.
Because it would be 0 plus 0 plus
Exactly, right? But now you're in terms of x and y. So now you would be going here, here, you would go over d now, and then you'd be saying what, 1, right? dA,
And then the 5 in front.
and yeah, the 5's out here. Now this just happens to be the same answer. This is the area of this thing now,
Yeah.
right?
Instead of,
That. But this would not be 1 had this not been flat.
yeah.
Yeah. Yes.
That same question that like he was having.
Mm-hmm.
It's like you have it down to like this, but like when you have like D, DA,
Yeah.
it's like
So at this point, what's z?
5.
5. You can replace that with a constant at this point, right? So you've got 5, you can pull it out, and then you've got 1 ds.
Yeah.
So that is the area of S, if you know it. If we know it, we can be done, which we do because it's a flat circle, right? But that's not your question, I don't think, right?
No.
No. Your answer is, so at this point right here, all you did was that part, right? So you're still doing a double integral over S ds, right? You wound up determining that that's basically 1. 5 comes out, right? So now you're here. So if you look in your formulas at formula B, right? You're basically doing formula B with the f of x, y, z being 1. And so what is ds in formula B? In order to change it over, that ds is the square root partial g with respect to x squared plus partial g with respect to y squared plus 1 dA, right? And then that becomes d. And d is your restrictions on x and y, whatever those are, right? So that's how you get from from ds to dA. You have to include this. It just so turns out, though, in this problem, this surface is a constant function, and so these become zeros, and you get square root of 1. So you get 5 d1 dA now, which is the area of D, which you again can just look at. Does that help? Had this surface been not constant, then to go from S over ds to dA, you'd have to do this part. That help? Okay. And even if we got to, let's say we got to this, let's say we got to here, and this wasn't, let's say this was x, let's just say it was in there, then we would need to do this part, which means we'd have to go to polar. Yeah. Just because of the way it looks down there. So we're getting, yes, you have a question? Okay. Okay.
We got 400 pi.
400 pi? I don't know. What are y'all getting? 80 pi, negative 160 pi, and 800 pi?
400 pi.
400 pi? So what did you get as your curl?
For the curl, we got as it was,
5G, right?
yeah, that's
5Z?
times the normal vector. But for the curl itself, it was e to the xy minus 2x, y minus e to the xy, then z.
So you got 5z for your curl?
I mean for the dot product.
For the dot product, of the normal
Why
vector.
are
and
you
the
using
curl.
your normal vector as 0, 0, 5?
Because isn't the normal vector of the circle, considering it's going to be it's still just a flat thing along
Sure.
5. It would
Sure.
be just a normal vector of the normal vector would be just 0, 0, 5 because it's along the z-axis going up 5 units.
Agreed, but why 5? It needs to be a unit vector. That vector has a length of 5.
Oh, okay.
So 0, 0, 1.
Oh, okay. So
Okay?
it's-
So if you do 0, 0, 1, how will that change what you'll have in there? It'll just be z, right?
Yeah, it'll just be
And z is 5.
So it'd be z would be 5, and then 5 that it would be
5 comes out, and then you're doing the area of that
16 times
surface,
8 times 80. So it'd be
80.
pi.
Okay, so that fixes it then?
Yes.
Right? Yeah, because you had 400? Did you figure out what?
Well, I got negative from up here when I dotted them. I used the -1 for the...
Is this 2z minus y or 2z minus, what is that? 2z right there minus z.
Z. Oh, whoops.
2z minus z, yeah, that's going to change your life significantly. And this right here, your normal, you should point it upward because we're moving around this way, right? Going this way. Then you want to be walking so that the surface to your left and that the normals are like sticking up as you're walking. You used those.
Yeah, I thought it was to the right.
Yeah. As you walk around, you want the surface here, right? Always to your left, and you want the normals there. So that's okay. It just changes it by a sign. But it makes this a lot easier. You don't need any of that. You don't never need to go to polar because when you do this right here, you're just going to get like 5z. Or no, you're just going to get z. And z is 5 because of where you are. And now you're just finding the area of the surface times 5. Yeah. Okay, I have another one for you. Oh, do I need to work through that? Do y'all want me to work through that or not? I'll just set it up real quick. The curl of f you get here, according to all of you, is the curl should just be something, something, and this last one should be 2z minus z, so you just get z. Agreed? And the reason why these first two components are going to wind up not mattering is because the unit normal vector for this surface S is the vector 0, 0, 1, pointed straight up. And then when you do this formula where you dot the curl with the n, when you dot this vector with this vector, all that winds up happening is you get the z. So what we're doing is the surface integral over S of z ds. So I'm using this. And z is 5 because your function, your surface here is 5 always. The z coordinate is always fixed. So this becomes 5, and I pull it out. And at this point right here is where you can stop and just basically say, hey, look, this right there is the surface area of S. And because it was a circle up here, pi r squared, the radius is 4, right? Yeah, radius is 4. So this area is 16 pi. So this is 5 times 16 pi, which gives you your 80 pi. Okay? Last one. Last problem of this semester, actually. This is it.
What?
What?
Is this the end of the chapter?
This is the end.
So we're not taking the file. So we're not taking the files?
That's the last problem I'm doing with you. So why don't y'all see if y'all can do this one? You have 20 minutes. See if you can figure this one out. Same thing, okay? I mean, you just run through the same process. You want me to help with the picture? Or?
I'm sure, why not?
Yeah, y'all want to see it? You got a plane, right? Your curve, okay, your curve C is the intersection of a plane and a cylinder. So we got a plane. We've got a cylinder, x squared plus y squared is 9, which is vertical, like this. So wherever those hit each other, this is going to be some curve. Now this curve is not, be careful here, this curve is not, flat. It's not a circle. It's like an ellipse. So if you ever get to the point where you get like, this is just the surface area of S, you're not going to know that, right? Unless you have a formula for the surface area of an ellipse, which they exist, but it's not something that you just know right off the top of your head. You have to know like the different vertices and stuff. Okay, so that's the picture. This is C. And C is the boundary of some surface S. Yeah. Enjoy. So what are we going to do on Monday then?
They would just actually decide the problem and have to review, and then half the people won't show up. Another fourth won't even care about the review. And there's only going to be about a fourth that actually do care for the review.
Okay. All right. So I should be here, yeah? No? Yeah, we will spend Monday reviewing, and what I'm hoping you'll come in with is questions. Last time I spent the end of class talking about what you should expect on the final. So you've got the whole weekend to go home and iron things out, figure out where you feel like your weaknesses are, and then you can come in and just ask me some questions, all right? All right, let's see if we can knock this out in the next 15 or so minutes. We meaning you. Any progress being made?
We found the curl and we started to be able to find a process to figure out the normal vector.
Okay.
That's what we're at.
Let's see here. Anyone need a hand or have a question or want to clarify or?
Yeah, that was the curl we got. However, we were working on finding this process for the normal vector.
You know the normal vector. It's close to what you were thinking.
We need this in 2 terms.
What were you thinking?
I don't think we're thinking the same thing.
We were. What were you thinking?
Just like 1 on 1.
Okay. That's just not a unit vector.
And so then we would just be 1 over the 4.
Yeah, because every normal vector on this ellipse, even though it's an ellipse, is still part of the plane. Right?
Yeah.
Yeah.
I just realized.
See, I told you I knew what you were thinking.
Well, how y'all got that one? I was like, oh shoot, it's root 3. And it's for the root 3. This is for x and y, correct? Or is it for? That's for all of them. Oh yeah, because the z is included. Yeah, the z is included in that. Yes, okay. So they have a normal vector. So you have 0 x squared plus, and then you have a normal vector. That normal vector of 1.
I thought it was
3. 3.
Oh,
That's what you got.
Yes.
So once you get to that, you would have to turn it. You have to turn x and y into terms of u and v, right?
Well, it depends on how you want to draw that surface, and it depends on whether or not you can use a shortcut. So at this point, you're working off the first few formulas because now you've got surface integrals. You've got some function of x, y, and z in front of ds. So you've got one of those, right? The question is your surface a surface that you need to get u and v to draw it, or can you do it this way? Can you draw your surface using one of those or the 2 on the back side? So is your surface S, can you look at it as a function of x and y? This? What function? The plane, right? So you just solve that for z, right? And so you're in that formula B, right? And that way you can get everything in terms of x and y. Your double integral will go over d now,
So
right?
this would stay the same.
That stays the same.
You would put another radical 3 out in front.
Yeah, you could, well, is it going to be?
Yeah, 'cause
Should
1
be,
minus
root
x
3,
minus
yeah.
minus y.
Yeah, so you're going to wind up getting the same thing.
Got that.
Yep,
dA.
yep.
D.
So go ahead, yeah, write it down, and then the question would be, yep. Which means you're going to need to do polar. There you go. Move that up.
That's what I got.
Brenda, did this one make more sense on the DS? Are you past the DS part, or did you get to that?
Yeah.
Okay.
We got to that.
Okay.
Yeah. And then we weren't sure like what functions we had to put in terms of like two variables.
Mm-hmm.
And so
What are you thinking it could be?
we went with the cylinder, but now we're not sure.
So the cylinder, that surface is this one, right?
Yeah.
You're trying to look at this green one, which the green one's going to come from the plane, right?
Well, let me put this in. We have this.
9?
Yeah.
That's only if you were living on the cylinder. You're not, this is only the boundary this way, right? What we've done, well, let me see if everyone's, maybe I can walk through this because we only have 5 minutes. So trying to find this, which means we turn it, I'm going to turn it into this one because we can find the normal vector of the surface, because the normal vector of this surface S actually comes from the plane equation, and Danny said it was 1, 1, 1, which is correct, but we have to scale it to make it a unit vector, so we do the vector 1 over root 3, 1 over root 3, 1 over root 3. The curl I think everyone had. So when we dot these two together, we should get this right here. So we have double integral over S of this with respect to surface area. Now, at this point, you're on the first page of the handout today. You can use formula A, but the easier way is to do B, because your surface S can be looked at as a function of x and y if you take the plane equation, solve it for z, and call that your function of x and y. So then that formula, or that turns into this part B, which is double integral over d, pulled out the 1 over root 3 on each one, and then ds becomes this, and then this is your g, so you take your partials and square, and you should just get a constant under here. You should get root 3, and then that's going to come out and cancel, and so we're stuck here now. And at this point, everything's in terms of x and y. The d we're talking about is the domain of that ellipse on the ground. So now if we project that onto the ground, this domain down here, that's d, and that's a circle on the ground. So you have to go to polar coordinates now. So that means x will be r cosine theta, y will be r sine theta. Yeah, that's going to wind up being r squared, but this can go from 0 to 2 pi, and r is going to go between 0 and 4, because our radius, no, 3, never mind. And 3. So now that double integral right here becomes double integral 0 to 2 pi, 0 to 3. That's r squared. But then we have an r from polar, r cubed, and then dr d theta. And that, I think, will work out pretty good. We'll just finish it. I'll separate it. Integral 0 to 2 pi d theta times integral 0 to 3 of r cubed dr. This one's 2 pi. That one's 2 pi times, and then this is 1/4 r to the 4th. I plug in 3. 81 over 4? No. Yeah? No. 3. 81 over 4 and plug in 0. So 81 over 4. And then, so 81 over 2 pi. All right. That's it. So we have mini exams. There's 2 of them still out there. Those are both due next Wednesday on the day of the final. Oh, I have them. Yes, I have those. And the bonuses, if you turned in a bonus. All right, so the bonuses are, here, I'll put them over here. The bonuses are here if you want them. And I put on here how many points I added to which mini exam. And then the mini exams are here.
About what we're going to be able to bring to the final?
Yeah, so what did I give you all for the second exam? You had a cheat sheet, right?
Yeah.
So you can bring to the exam anything that's on our website in terms of formulas. You can bring anything that I've given you as a handout in class, all right? In addition to that, make one extra sheet of just random information that you feel like is important to you. Just don't work problems out, all right? And we can talk more about that on Monday, but at least for the weekend, you know, if you want to start putting something together, you can. All right? All right, turn my camera off.
We only do 4 mini exams, right?
You only had to do 4, but I think I said you could do up to 6.